Good morning, everyone. So in this talk is going to be a bit about the intersection of model checking, temporal logics, with some applications to graph transformation, and also using a bit of categorical semantics and categorical models for this logic, and also the use of proof assistants to use this logic in practice. So to summarize, what we're going to see, we basically, in our work, we present the semantics of a temporal logic using the counterpart paradigm. I'm going to explain what that is in a bit. And that allows us to reason on the evolution of graph-like structures, so anything that can be actually expressed as a multi-sorted algebra on a signature. And we formalize the semantics and the models of this logic using the algorithm of the system, along with some results on the positive normal form of this logic. We're going to start with some different review of temporal logics and the counterpart paradigm. Then we're going to switch to the semantics, both classical and categorical. And we're going to see some examples for the normal form. Then talk a bit about AGDA, and then some conclusions in the future. All right, so a very brief introduction to temporal logics, just in one slide. Temporal logics are very well-known formalism that allows you to specify and then verify from systems, complex systems like computer systems, for example. And the idea is to represent the system as a transition system, right? Which we call the model. So, for example, we start from the paying state of a simple vending machine, and then we select our beverage, and depending on our selection, we can either be in the tea state or in the coffee state, and then we go back to the payment state. And then the second step is to express the properties that we want our system to verify as formulas in some temporal logic. For example, we can say that always, eventually we end up in the state of pay, right? No matter what path we take along this graph. And it's not true that eventually we get into the T state, right? Because we might, for example, always just select coffee and loop into the second part of the graph. And then the third step is to use a program to check that this model satisfies these formulas, right? This is what model checking is all about. But as we've seen, states so far are only simply atomic points, right? So they're not decomposable into other parts. But in practice, the system that we're interested in can often have a structure, and that changes in time. Right? So, for example, we might be interested in modeling the states as graphs. So the state of the system is a graph, right? And then we can want to express during its evolution that nodes can be merged together, or edges, for example, in the graph can be deleted, and that expresses the evolution of the graph in time. And processes also, for example, are a very good example because processes fork in memory, right? So they evolve by forking, by being deallocated. So they disappear out of the system. Or, for example, electron rhythms are a nice example. Right, so the parties can split, unify. So how do we enrich the models that we were working with to express this kind of multi-component behavior? And how do we define these logics that can express properties on them, right? And they can also refer to individual elements of the state of the model. The answer for us is yes, and the counterpart paradigm is one possible solution. And counterpart quantified temporal logics are another approach, the syntactical version that we use to reason on the models. So in standard LKL traces, for example, if you're familiar with that, the model that we work with is basically a trace. So it's a sequence of states, and the properties that hold at a given state, which we indicate here with them being colored in red or blue, are on the state as a whole, right? So it's atomic. But the approach we take is that instead of just having an atomic point, we associate to each state, which we call to each state, we associate a set of individuals, okay? And we call that a world of individuals. For example, in our case, we associate this world to this state, this world of 4 individuals. And now you can see from the picture that the properties are not on the state as a whole, but on the individual elements of the state. And as indicated by the color, right? So, for example, C0 satisfies the property of being blue. And the question is, how do we represent the transitions from one state to the other? And the idea of the counterpart paradigm is to use something called counterverb relations. And relations are really to be intended as subsets of the Cartesian product of the set, right? And the idea, the intuition behind this is that individuals are in each world are connected by a relation if they are the same individual after one step. So we carry the identity of an individual onto the next world by connecting it with our relation to the next. And we say, for example, that A1 is a counterpart of A0, and A1 is a counterpart of B0. And so they are the same individual that gets merged into the same at the next step. And these are relations. For example, we can have B0 duplicates into two counterparts, B1 and C1. And we call these sequences of worlds and relations between them counterpart traces. Right? So just to be a little bit more formal, we can imagine this model as being a function from rational numbers into any set. And then we have a family of relations indexed by I between one world and the next. And actually, you can generalize the setting. Instead of just creating sets, we can take algebras over a multi-story signature sequence. And in particular, we take sigma algebras, so as models instead of just sets, and we take structure-preserving relations between them. So we can either consider relations, or we could also consider functions or partial functions, if we want to exclude, for example, duplicating behavior. And as example of these, we have graphs. Under red graphs, we can also talk about trees, lists, etc. For example, also abstraction industry, for example. And this, for example, is a counterpart trace on the signature of the directed graph. So each world we associate an algebra, a sigma algebra, which in the case of this signature of the directed graphs, we actually have a graph for each world, for each state of the trace, right? And then as data of our model, we're going to be having a relation, a counterpart relation between the nodes, first of all. So for example, you see that each node here has a counterpart into the next one. And for example, N4 is the counterpart of 0. And then we're going to be having another counterpart relation between the edges of the graphs. So for example, we have E0 has a counterpart E4, but for example, we see that E2 does not have a counterpart. So that effectively, the model tells us that the evolution makes it so that E2 is deleted, right? So it's deallocated. And these need to be structure preserving. So for example, if we have a counterpart E0 to E4, we also need the source of the edge and the target of the edge to be counterpart related, right? So that we respect the output structure. Right. So you've seen the notion of counterpart trace. My counterpart model is just a generalization of that, taking transition system as using worlds and connecting them. And actually, the data that we've talked about can be actually packaged up in a neat way using category theory. And if you're familiar with that, we can say we package this data as follows. A counterpart model is just a category, any category, a specified class of morphisms of W, which we call temporal structure, which identifies the one-step evolutions of the model. And then, in the case of sets, for example, so without talking about graphs for now, the data is exactly a pre-sheaf on this category into rel. So rel is the category of sets and relations. And we call this a relational pre-sheaf. So the intuition is that each object of the category is a state of the transition system. And the morphisms of the category are the transitions between states. And you see how the pre-sheaf gives us exactly what we want, right? A relation between the sets, the worlds. And the temporal structure identifies, as I said, the one-step transitions of the model. So we want to restrict our attention to just some morphisms, not all of them. And we're going to see later graphical intuition for this. And as I said, relational pre-sheaf gives us the states, so the worlds to each state, and the transitions between them. So graphically, so we see here just a category, and in red here, for example, F, G, H, and K are denoted in red to indicate the temporal structure. So those are the transitions of the model we're interested in. And a relational pre-sheaf, it gives us exactly this data, right? So to each role, we want to associate a set, and then the fact that it's a functor also makes it so that the composition of the counterpart relations is also part of the model, because we are going to be considering that in our logic. And for the signature of directed graphs, I'm going to just give an example of the story signature, is that the idea is that we're going to be having as many relational pre-sheaves as there are sources. For example, we're going to be having a sheaf for nodes and one for edges, right? And then we're going to, for each function symbol of the algebra, we're going to be having something called relational morphism, which is actually not a natural transformation, so it's not a morphism in the functor category. But that will give us exactly the data that we're looking for. So just to give another example for the other running example for graphs, we're going to have one presheaf for the edge sort of the algebra, and then we're going to have one for nodes. So this gives us exactly the same data, and then we're going to be having the relational morphisms to connect, right? So for each edge, we associate both a source node and a target. Now, the fact that we work with WL in this case is not really important because it's a relative dual, but that gives you intuition. Right, so now we're going to be specifying our logic and its syntax. Okay, so in particular, it's going to be sort of a variant of LTL, but using a quantifier. So it's a quantified temporal logic, and we define the models of this logic as the traces. Right? So we're going to be starting with just the usual propositional fragment of the logic. So true, for example, negation, conjunction. So we have all the other classifiers, classical logic in this case. Then we're going to be having the next operator and the until operator. We're going to give a semantic for that. And since it's a quantified logic, we're going to be having existential quantifiers, one for each sort of the signatures. So we're going to be saying there exists a node in this world. Now we can see how that translates into the intuition. There exists an edge in this world, and such that phi is satisfied. And then we're going to be augmenting, let's say, our logic with a unary predicate. That's going to be for to show some examples, right? We're going to be coloring edges and nodes with some color, and that's syntactically what this represents. So we're going to be saying an edge, a node is blue, right? And actually, we're going to be having elementary formulas that we add to the mix. So elementary formulas are actually equalities, and they're type equalities. We can express the two nodes that we have in the context are equal, or two edges are equal. Right? And the grammar to specify what a node is, for example, it can be either a variable, which is going to be typed sort, or it can be the source of an edge. Does that make sense? And then an edge is just going to be an edge variable. We don't have any other way to express it. It's fine. Obviously, we can also add constants, but then you need to change the mods. So the semantics of this logic is going to be defined as follows. So given a trace sigma, we define a satisfiability relation on tuples of nodes and edges satisfying phi. So this is pretty standard. And in particular, tuples, by tuples, I really mean assignments, right? Because we're going to be assigning to each free variable of the formula the specific node and edge that it corresponds to. So for example, I'm just going to go quickly through these. We have the true is always satisfied, conjunction if and only if both of them, and then equality is going to be defined as being true whenever their interpretation of this given assignment mu, given the trace and the assignment, if their interpretation is effectively the same, right? They refer to the same action. And for example, existence is defined as if there exists a node in the current world of the trace, right? So sigma is going to be the trace, and omega 0 is going to be the first world of sigma. And here we're talking about the set of nodes in the first world, such that extending the assignment of this node gives us something that is satisfied phi. And so phi has a one free variable than this entire formula, and so we must extend the assignment. And the interpretation of next and until, so get to the actual temporal operation, is pretty interesting. So we define next as being the following. If there exists an assignment mu1, so in the next world of the trace, so not the first, but the second, if the second assignment is counterpart related to the first, okay, this is how you read it. And C0 indicates the first counterpart relation to the trace. And then we want the new trace, after eliminating the first world, to satisfy phi on the counterpart related assignment. And assignments are counterpart related if their elements are counterpart related pointwise. It's a reasonable definition. And the definition of until is a bit tricky, but it's basically the same idea. So there must be an n bar such that there must exist counterparts at all steps such that they satisfy the first formula. And at the last step, and bar, there needs to be this assignment here such that it satisfies phi 2. Okay, just to give an example, so we're going to be coloring, as I mentioned previously, for example, this node and this node to be red, so they satisfy the predicate red of x, where x is going to be a node. So this is just going to be the algebras, and this is the counterverb. So for example, we have that n1 in omega 0. So the first world satisfies next loop, because there exists a counterpart in next world such that it satisfies loop of x. Or obviously, here I'm going to be using a bit of syntactic sugar to indicate x is going to be referring to the first variable of the assignment. But for example, we have that n0 here does not satisfy, well, it does satisfy next, right? Okay. It's a bit of a typo. So then we're going to be having that n2 satisfies the formula red until blue, right? Because there exists a counterpart here, and then there exists a counterpart here, such that red is satisfied all null world before the last one, and then in the last one there exists a point in which it's actually blue. So we can actually talk about assignments, so we can have more than one free variable in the formula. So n3 here and n4 here satisfy next x equals y, right? Because they are merged at the next step. So we can express the merging of nodes in the graph. For the empty assignment, for example, in the first world satisfies this one. There exists an x, which is going to be a node in this case. It's not typed, but you can see how it is, such that at the next step it's blue, right? And for example, if we take n1 and n2, we have the formula that they are different nodes until there's a point in time in which they become the same, right? After some unspecified number of resolutions. And for example, we can exploit the structure of the graphs, right? So we can express we can say the formula loop of V, which holds precisely when E is a loop, so that the source of E is exactly the same as nodes as the target. So has loop is defined similarly. So a node is a loop when it has a loop, so there exists an edge such that it's loop, etc. And it's defined on the node we want to talk about. And we talk about two edges as being composable, right? So the source and the target must agree. We can talk about a composition. Oh, here it exists, and obviously exists an edge such that there. Well, actually, there's another part. Composable XY, so two edges have a composition if they are composable and there exists. Right? Just that they agree. And then we can talk about two nodes being adjacent if there exists either a node in one direction, an edge in one direction, or in the other. So you can see how it's pretty expressive as a logic. And for example, we can say that E4 at the next step becomes loop, right? It gets translated in its counterpart as E5. But for example, E3 here, you can see that it does not have a counterpart in next world. So in particular, it does not satisfy next loop of x. Okay? And E3 and E4, similarly, they are composable, right? And N0 and N2 are adjacent, these two, because there exists an edge. But for example, N0 and N2 are not adjacent at the next step because there does not exist not directly, right? And for example, we can also express with LTL. This is expressed eventually, and you can say that E0 after some temporal evolution, E0 to E4 to E5, it becomes a loop. Right, and then you could talk about the PNX, so it's just a presentation of the logic without negation, right? That is usually given to simplify model checking because you don't have negation. But you have to treat other operators as in return. And it's also used for fixed point semantics, so you eliminate main causes, fixed point failing. So PNF are actually also extensive to work in a proof of system, for example, ALGA, but we're not going to talk about too much about that today. And how do you get the PNF? So basically, you add all operators, so including the one you would obtain with negation. And negation only appears on elementary formula. So you have for all, you have the other version of the elementary connected. And then the interesting thing is that, well, let's say we have next until and with until. and that's an important detail, then you have there, if these are existential versions of the connectives, because we're asking that there exists a counterpart at the next step, then these must be the universal version of the quantifier. So we want next f to hold precisely when all counterparts at the next step have satisfied some formula phi. And that becomes precisely useful when you have universal and then you obtain these equivalencies, which allow you to express one in terms of the other and to push negation down to elementary form as you do in standard LTL temporal logics. And as I was mentioning, these quantifiers become especially useful when you want to talk about duplicating everything. For example, let's take another graph and let's connect first of all the nodes with counterpart relations, right? So we can see how we express already duplication of nodes, right? Duplication and then merging. And then let's add counterparts to the edges. So you see how we can also duplicate edge and assign its identity to the next world once we give a counterpart relation for them. And for example, N0 satisfies next for all. That's how you read next F. Next for all blue of X, because all the counterparts for N0 in the next world satisfy blue. But N1 obviously does not satisfy, because N4 does not satisfy blue. And E5, interestingly, does not have a counterpart. So it still satisfies next step, obviously because the for all is vacuous. And for example, you also have, let's take this a bit more complicated formula. So here we're talking about the source of an edge, right? In this case, E1. So we want the source of E1 to be blue, right? So that's true. And until in this case is the existential version, right? I will put the F. So we are asking that there exists a counterpart at the next step, such that blue is still the source of the edge is still blue, and then it becomes a loop, and then we don't need to ask that it's a blue node. But it does not satisfy the for all version because E5 does not work, right? Because it's not blue the source. And then we can also talk about weak until, and if you know about a bit about LTL, then weak until basically says you can always just have this holding for all the worlds in the trace, and you never get to this point. It's never satisfied, but this one is satisfied. Okay, now we're going to be talking just very briefly about Agda. So Agda is mainly a proof language and proof assistant, right? Because it works under the text proposition paradigm. And it can be used in practice to formalize mathematical constructions, for example, the semantic syntax of this logic. And so we basically formalized the categorical version of QLTL and its models in Agda, using the Agda categories library to capture the notion of category theory in this context. And we've actually formalized the version in which you can have the logic as being over any multi-story signature. Right? So you specify the signature, and then Agda gives you the syntax and the class of models you want to work with. And also a classical set, more classical version of the logic, so that it would be more appealing for someone without a categorical logic background. Right? And then also polynomial forms of QLTL and some theorems that don't hold any. We talk about relations and polynomial forms. So here's some stats for the formalization. And why is the formal presentation of this logic useful? Well, because it establishes their correctness. You can formally verify them, right? And then it actually gives you a playground in which you can actually test and experiment with these temporal logics. And it also establishes a foundation to build the model checks that are actually verified because it's semantics from them. And also, it gives you a program that can convert the standard models into the category. Right. So I'm going to skip this part for in the interest of time. And basically, these are some. It is a summary of the results we have for the conversion between QLTL and its PNF form in the case of partial functions and general relations. And the main takeaway is that LTL-like expansions break down in the case of relations. So if you have partial functions, you can actually recover some of them. For example, the expansion of. Right. So just to conclude, so as we've seen, I just give you a brief introduction to a counterverb-based temporal logic that allows you to reason the structure control of algebraic structures, like for example graphs, and some possible extensions we would like to work on is the formalized QLTL on the second order. So instead of just quantifying on individuals, you can quantify on sets. There exists a set of individual subjects in problem. And obviously that's going to be explained in terms of complexity, right? And then you can also consider, instead of it's a very general framework, you can also consider CTL, CTL stars, and other logics, same paradigm. And also it would be interesting to interface our proof assistant with other SMP solvers such that the proof actually gets computed more easily, right? Because you have a model checker that can actually go and verify the model you specify. And it would also be interesting to formalize not only the models of the logic, but also the syntax of the logic using index categories and morphisms between them. So I'll be talking about an initial model. And study of formally presented temporal logic is still absent in the literature, but there is some work, for example, in Isabel for LTL and ICOF. And there's another interesting work to verify CTL in the concept of functional reactive programming in Agda and Pisa. And that's it. Thank you.
So some time for questions. Questions.
Yeah, just curiosity, but you said you formalized it in Agda. Did you choose Agda for a particular reason? Do you have some libraries or something that made it easier to do in Agda?
There is no particular reason that makes it easier to do in Agda, to be honest. So maybe because I'm more familiar with it, and also because I'm more familiar with the Agda categories library, because it's what we're actually working on. But other than that, it would be also interesting to see mechanization procedures in other proof assistant, for example, Cock or Isabel, would actually help in verifying.
And we can ask the next speaker to comment on this after this talk. Are you standing by for the next? Yeah, sure.
So the main reason why you have this category is that we want to use the category library because I didn't understand what you gain from the category.
It's more the other way around. Since we had the categorical semantics to begin with, we want to formalize that also. Yeah. But we work with categorical logic because it makes things easier to work with, if you're category theory, but also because this connection between the counterpart paradigm was actually something in the 1960s in philosophy, like the view is actually something that didn't have a formal semantics. We just found the categorical models simply to work with.
I did have one question myself. So in your model, it is allowed to duplicate nodes, but also for nodes to spontaneously generate and for nodes to die. Now, in your logic, I didn't see a way to refer to that. So did you think about it? Can you express that a node no longer exists or that it has just been generated?
Yes, you can. For example, you can just say next true. That's you can refer to next true. There are some subtleties to that, but you can definitely refer to, for example, in the paper, there's a way to refer to next step be allocated or next step be reserved. Okay.
No more questions. So thank you very much, Andrea. For the next presentation, and while you are getting your slides, this is of course, the paper that we learned this morning has actually won the best paper award of the EASST, the theoretical best paper award for ICGT. I'm sure we are also very much looking forward to learning what you have to do to write the best paper. It's worked together with Detlef Plump at the University of York, not all that far away from here. And now I've talked so long that you actually have your slides. I'll see the title and I'll take it away.
Thank you very much. It's a pleasure to present to join work with Söldner. And I would like to start describing the story which he did. So while I was walking through the literature, I encountered a paper from Barry Rosen, and the details of what is shown basically is not important for our discussion. What's important is the highlighted story, which is this is really very intuitive. And this caught my attention and it made me actually smile. And the reason is that this requires a lot of personal trust in your personal skills to fill in all of the intermediate steps proofs. And so just it's clear. I'm not questioning the correctness of this paper. It's about the phrase itself. And the point I want to make is that you have to trust the author, or you have to fill in all the gaps, which is probably quite difficult. And the step toward more increased confidence in the proof itself is to use proof checkers. Especially interactive proof assistants might guide you through the way of proving. So in general, proof assistants are used in two main application areas. One is providing machine-checked theories, such as the four-color theorem or our work. And the other one is verifying software components, such as file correctness verifications. And our motivation is to certify the basics of the TPO theory in the Isabelle proof system. And we are aiming for establishing a framework for verifying GP2 programs. So verifying specific programs which consumes input graphs, performs them input-output graphs. And my hope is that after this talk, I will be able to convince you that proof systems are mature enough and can be used in verifying trusting properties. So I will start with the basics, a graph. We're interested in labeled graphs, which are finite and directed. It's, I think, a pretty common definition. And I will jump directly into how we encode graphs in Isabelle. Obviously, there are many different ways of encoding it. And this was initially a surprise to me, and probably to Detlef as well, that you have a lot of freedom. So what we adopted is a way in which we have two stages. So we start with a record type, a polymorphic one. So type errors are denoted by this small tick, which we call pre-graph. We call it pre-graph because you can, in theory or generally, represent invalid graphs with this structure. For example, just an edge. And we have basically the same properties. Nodes represent as a set over some base type, a source function denoted by Isabelle Hall's function type. And to enforce all the correctness properties of the graph, we use so-called locals. So locals are a mechanism for structuring the proofs in Isabelle. And using the fixes keyword, you can introduce parameters into your local. And as you can see, we still treat the types of our nodes and edge identifiers abstract. So we're not saying what they are, and nor are we talking about concrete labels. We still keep them abstract. And using the assumes keyword, you can specify local assumptions, like axioms, which are always valid within the local context. And using, for example, using this syntax, you can define names referencing certain facts. So the finiteness of the node set using the built-in predicate finite expresses its property. And you might have noticed, sorry, the Counterverb case. Basically, this is a type class restriction of the type representing the node and edge identifiers. And this is a requirement because Isabelle's local mechanism restricts the introduction of new types in certain situations. And in our formalization, all graphs might have different types to represent the node's edge IDs. And this is especially relevant for the gluing and deletion construction, where we use the sum encoding to represent the disjoint union. We changed the type by our gluing construction, and this is forbidden in Isabelle. And it's some sort of limitation of and it hits us when we try to define and interpret the universal property of push-outs. So the solution to overcome this limitation is to use just natural numbers to identify nodes and edges, and require this countable instance, which provides us with a way of an injective function to map into this representation. And for simplicity, we introduced a type synonym which just interprets the pre-graph using natural instance. So moving over to Graphmorphisms, we follow a similar approach. So Graphmorphism comprises of two mappings, one for the nodes, one for the edges, making the diagram mute. And we basically represent it similar. So we have a record type now already with two type parameters for the nodes identifiers and edge identifiers. And we again enforce all the properties using the local mechanism. But here we start to use inheritance. So we inherit the properties of the graph local for the parameter G. So what we can do with it is we can bind all of the graph properties stated in the local graphs and bind them to the name G. So for in later proofs, we can refer back to these statements. And you can see that the countable type class requirement propagates through our code base. And we fix the parameter of the local morphism record type again, and we state the usual assumptions. Now moving to rules, we follow the exact same approach, a record describing left and right interface graphs. And you can see here already that the amount of type variables is increasing. And this is to one extent it's a downside. To the other one, it helped us in the development process because you're not able to mix identifiers because the type checker observer will prevent that you actually mix by accident different IDs from graphs. For completeness, if you want to, or we define injective morphisms by inheriting morphism properties and adding additional axioms like the injectivity of both mapping functions for the source set. Now rules can be represented by two injections from the interface on the left-hand side and from the interface on the right-hand side. And by using the for keyword, you can annotate types. Sometimes you have to do it. In this particular case, you have to do it, and it is getting bigger and bigger. For later views, we need the concept of pushouts. So given A to B and A to C, the graph D, together with B to D and C to D, it's a pushout if and only if this author diagram mutes and the universal property is satisfied, which says that for all graphs D prime, there exists this unique isomorphism, unique morphism, which makes the author diagram mute. And in our formalization, we formalize two different views of direct derivations. We formalize an abstract view, which is obviously based on pushouts, and an operational view based on doing construction, so set-based construction. And this operational view has been presented last year at the GCM conference. And today we focus on the abstract view based on pushouts. And the direct derivation can now be nicely described using a rule, using inheritance of a rule, an injective match on the left-hand side to the graph G, and the two corresponding pushouts. And one important theorem we have proven in Isabella is the uniqueness of direct derivation, which was first introduced by Rosen in 1975. And it says that if you have two direct derivations, 1 and 2, and 3 and 4, push-out complement is isomorphic, so unique up to and H as well. And in this presentation, I will focus on push-out complement. For this, we need the notion of pullbacks. So pullbacks are the dual construction to push-outs, given B to D and C to D. The graph A together with A to B and A to C forms a pullback if the square commutes and the universal property is fulfilled, which is for all graphs A prime together with A prime to B, A prime to C. There exists a unique morphism A prime to A, and such that this triads commute. And we need the notion of composing and decomposing push-outs. So if we know that 1 is a push-out and 2 is a push-out, we know that the composition is a push-out. If we want to decompose and know that 1 is a push-out and the composition is a push-out, we can conclude that 2 is a push-out. And for pullbacks, it's similar. If we know that both are pullbacks, we know the composition is a pullback. But for the decomposition, it's the other way. If we know that 2 is a pullback and 1 and 2 are pullbacks, we can conclude that 1. And to show you how we encoded Isabel, we stated this as a lemma, for example, of the first statement. And using this use keyword, you can describe assumptions of your lemma. And the push-out diagram local also provides us with some predicates, which allows us to write it the way we do. So we're saying that this set of parameters satisfies all of the push-out diagram local assumptions. Then we're able to show that the composition is also and for the final proof, we need the push-out characterization and the reduced chain condition, which have been introduced by Erik and Krosky in 1979. And the reduced chain condition says that for all elements B and B and C prime and C, such that they project the same element in D, there exists an A, and such that the postmorphism projected to the corresponding B prime and C prime. And for the push-out characterization, we need the injectivity of the morphisms, that the diagram itself satisfies the reduced chain condition, and that G and F are jointly subjective. And with this, we can start looking at how we prove the uniqueness of the push-out complement. And here we follow mainly the proof of Lack and Oshinsky from 2013. But instead of the one-count property, we rely on the push-out characterization. And the general idea is that you construct this proof with 1 and 3 at the bottom. So 1 is at the bottom, and 3 is on the left side. You construct the pullback of D prime and D, and then you need to show that D prime and D are isomorphic. And we do so by showing that K and L are projections. And the general idea how to show it is to show that the top face and the back right face are push-outs, and since push-outs preserve projections, and on the opposite side there is the identity function, we know that K and L are projections. And just to show the first step, if we start with the back left side, we see that we have on 3 corners K with the identity function and 2 injections B. This is a special form of pullbacks, which we have shown, Isabel, which are always, such a structure always satisfies the pullback requirements. And then we need to show that the back right face is also pullback. And we do so by starting at the front left face. So this one, and it's an injective push-out. And so we know that it's also a full deck. And then we can compose it with the back left side. The composition itself is again full deck. Then we can construct H by using D and D prime. And as the top and bottom commutes, we can conclude that the front and the back right is also a full deck. And by decomposition, we know that the back right is full deck. And then we can use the push-out characterization to show that the back right face is also a push-out. And then we can use the trick that on the opposite side there's the identity function. That L is projection. And we can do the same for K. So we want to show that the top face itself is push-out, which we find by the push-out characterization. But we start with the bottom face. It's an injective push-out, so we know that we can compose it with the back left one. And as we know that the front commutes and the top fallback commutes, we know that the front and the top one is also fallback. And then we can decompose it to know that the top face itself is fallback. And then we need to show the required properties like H is adjective, and jointly is subjectivity of D prime and K, these two, which we do by looking at how we construct the fallback and the two reduced chain conditions, which are always satisfied by injective fallbacks. And then we know that the top face is push out, then we can use the same trick to compute it. The inverse composed with K is projection, then we have shown that these two are isomorphic. Moving on to parallel independence from Ilikovsky from 1976. So given these two direct derivations, say that they're parallel independent if there exist these two morphisms, such that they commute with them. This one. And now we can state the final theorem. So given these two direct parallel independent direct derivations, there exists a graph G prime such that those roots reach the same graph. And we do so by decomposing pushouts 1 to 4. So these four. And basically rearranging them. So this is a copy over from the previous slide. The idea of the vertical decomposition is to construct the full deck 12, so this one. We construct this D. So it's full deck of D1 and D2. And then we need to show the existence of K1 to D, which follows from the universal property, the first push out. And D to D2 and D to D1 follows from the construction. And as we know that one is the full deck, because it's an injective push out. We know that the composition is full deck, and then we can use the full deck decomposition and use again the push out characterization to show that 11 is a push out. And then we can conclude that 12 is also push out. Now it's a matter of just reordering all the existing push-outs and using the gluing construction for push-out 5 and in the state where you have two sequential direct derivations leading to the same graph with different push-outs. And with this, I would like to highlight what we are aiming for in the future. So we want to develop our formalization further so that we can support attributed degree graph information. We want to formalize GP2 semantic, and you can see one example of the GP2 program below, which computes the transitive closure of some input graph. And we want to formalize our calculus presented in 2021 ICGT. And I would highlight that our end was, we aim for verifying specific GP2 programs. We want to verify specific GP2 properties programs. What's this? I hope I'm in time.
Means that we have questions.
Properties do you want to specify?
That's a good question. For example, if we want to structural correctness, for example, do you want to verify that in this particular case that all two pairs are linked ones? Yeah.
That's like all of the progress, not full correctness.
Final properties could also quantify something about labels and
These that's the cluster. In case you will be able to have that visualization.
I'm sure if you yes, indeed. The idea of this program is that it executes link as long as possible, and this is basically the link function with the negative application or restriction of application.
Yes. But when was attributed in the program always of attributed, it's not only attribute, it's also application.
More type questions, but I also want to check just with the next week. It's you. Okay. Yeah. Please go ahead. Andrea. Yeah.
For what I think I must say, I remember one detail a bit different. There's a church was assuming one was proved by Derivations and how I think only the second one is my impression.
Thank you very much. I was right.
Yes, that was we didn't find them. I think that's what I am. I really I don't think it's too long.
Okay.
This
is the archaeology of patterns. Yes. There was another question there. Yeah.
Okay, one of the dealing features is automation. Take the slides out. Did you use them? Did you think it out well?
Yeah, definitely. I mean, in the end, if you just use Söldner, and I was running into this issue, you get some roots, but it's very, very difficult to follow what actually happens. A lot of stuff will be behind the scenes, and it's extremely difficult to follow the rules. Still, Söldner helps you a lot on identifying the facts you have to consider, and maybe even in our case, which push-outs you have to look at, and which push-outs provide which information, and how you can stick them together. But we did not rely entirely on using Söldner, but Söldner provides you this benefits.
I was wondering, you made one difficulty that you had to solve because you were using the values, but this is used the
local settings, exactly.
Any other challenges? What do you have? What were the difficulties that you have to solve?
Let me go back to the first slide. The big challenge is to find a correct or a good representation. So there are many ways of representing graphs. So our first version, for example, just used locals and didn't rely on a record. And then you have to pass in 20,000 parameters into the locals, and it will be very, very large. And it's very, very difficult to name different facts after it. And another one is, for example, here we use just ordinary sets, but Isabel Hall provides you with finite sets as well. So we used this representation where we use the finite predicate to enforce it later. You could also enforce it on the type level, but then, at least in our experiment, the automation was limited, and several effects have been missing. So in the end, we decided to first start with.
I always ask, why can't you use finite set? They have done that, right?
Yeah.
Very different from this.
But you have to. Yeah. Actually, a lot of theorems have been lifted from sets into finite sets, but not all of them are there. So I mean, all is drawing, and everything was there. So in the end, we ended up with this. Also, we used total functions. We had one approach where we used the partial ones, which are emulated using an option type. And then the syntax will be, I mean, it works, but the syntax will be special.
So I think these are pragmatic lessons learned that are useful for anybody who tries to do anything like this.
Yeah, happy to talk about this in more detail.
Any other final question? Yes.
Did you address general matching or injected matching?
Injected. So in this book, everything is injected. Injected words and matching.
You have in mind why I'm going to also be fasting this week. I think about that, can also go to what does all.
That was part of the presentation.
Yes, it's right. I mean, at some point we started, and you know, we've proven a lot of push-out stuff, independent of the injectivity. But the final results are using injective words, and but certain push-out properties are proven within a general setup.
I think this is a good moment to stop next to me. Next speaker was Banach, if I pronounced that correctly. Yes. And we see all the presentation in this session about formalizing stuff on different levels. This is about formalizing bone graphs. And while Richard is setting up, let me give an anecdote. In the abstract, it says, unfortunately, presentation of bond graphs. I don't know if you've ever seen bond graphs. In presentation, bond graphs are replete with ambiguity significantly impeding understanding, and that is in mechatronics world. And there's only bond graphs, and I had greatest difficulty understanding what they were. And every time I asked a question about what does it mean, turns out it's not all that formally specified, or it's based on understanding. So I'm very curious to hear how that all that has been resolved. And again, I managed to talk you through the waiting time. So let me give the floor to Richard to
Is there a
about the
thingy to
formalization,
graphs?
refinement of bond graphs. Here you see this.
That's the full screen thing. Probably easier to do. All right, so this is coming up on Zoom as well now, yeah? I assume. Yeah. Okay, good.
Thank you. Well, thanks for the introduction. I'm very relieved about leaving the business from asking your colleagues from 20. I'm just going to say I'd have to be very careful not to insult people too much, but it's absolutely true. Bond graphs sort of seem to be almost like a sort of cult thing that you get into ways of doing things and you learn certain rituals, and if you learn them right, things work. And if you're trying to come to them cold from outside, it's very difficult to figure out what's going on. Anyway, this is joint work with John Baugh. Now, I'm a sort of computer scientist interested in formal methods, graph transformation. It's Very nice to be here after so many years not doing graph transformation, by the way. So I met a lot of old friends the last sort of day or so. John is a proper engineer. He's a civil engineer, right? So he's actually interested in bond graphs in anger, if you like, wants to use them, and has sort of come against these kind of brick walls that I've been talking about. So in the end, he kind of persuaded me. So I was a bit reluctant. I said, oh, to hell with it, let's do it, right? So see if we can sort of create an account of bond graphs which satisfies the sort of standards and rigor that we would find acceptable in the sort of formal methods or graph transformation community. Okay, so this is the sort of agenda. Talk a bit about the physical theories that are involved, and then go a bit deeper into the bits and bobs of bond graphs. And then how do you actually, so that's just descriptive stuff as you might find in bond graph textbooks, for example. And then we sort of approach the formalization. How do we build particular graph type structures that capture the relevant detail? And then we introduce a fairly simple category of these things and go on to the business that brings us to this conference, which is transformation. And then, as far as we're concerned, the main use of bond graph transformation is for abstraction and refinement. On a big system, you want to encapsulate parts of it and reduce it to a single symbol, for example, and you need ways of doing that. Well, bond graph transformation, it turns out to be the perfect tool to do that. So let's get going. So we're in this sort of mechatronic type multi-domain engineering world where you're engineering with things that you can see, that you can pick up, or that are too big to pick up, right? So you're not in the micro electronic kind of world. And it turns out, and this is the sort of profound observation around bond graphs, where's the thing? Does this work? What's the thing to? Oh, no. Is there a pointer here? There's one of them. Okay, so as I say, the more profound observation that led to bond graphs is that a lot of fields of engineering that are sort of in this sphere actually rely on the same kind of mathematics. So there's a sort of relationship between something I've called Q there, its first derivative and its second derivative, and it's driven by a sort of driving force E, okay? And the most interesting case, or the ones that are most discussed, is when this reduces to a linear constant coefficient ordinary differential equation system. So you see this thing here, that looks very reminiscent of something you might get in a sort of high school sort of electrics course or whatever, okay? And so they introduce sort of general terminology here. So we have generalized displacements. This is the fundamental Q variable. Its derivative is a flow, which is very important, and the generalized acceleration, which is the second derivative. And it's driven by this thing at the bottom called the effort, which is the right-hand side of this equation. Now, this, as it says there, applies to many, many engineering fields that are sort of typical mechanical, electrical, hydraulic, thermal, this sort of real physical stuff. But people have applied the same ideas to fields like economics and even biology. People have tried applying this to all sorts of things, okay? And the bond graph view basically says these complex systems are made out of discrete engineering components, so-called, in their terminology, lumped parameter devices. And these are connected together through power bonds and are otherwise isolated, okay? Now, anybody who's done any physics can clearly see in all these kind of fields that I've mentioned, energy comes and flows and so on. So that's a fairly trivial observation. The point is that you can actually deepen the analogy to the sort of lower level detail, okay? So these power bonds clearly have to be compatible. You can't connect an electrical connection to a mechanical one, obviously. So you need some discipline in here. The important aspect is the thing in the box, that the power is, if you express all these systems in the right kind of way, always the product of the effort and the flow. And the power is simply the amount of energy you're processing per unit time. Okay? So often in sort of discussing examples and so on, we stick to the very simplest kind of devices. So there are dissipators or like resistors, and they have this first equation there. There are things called compliant, so they're like capacitors, and they obey the second equation, and things called inerters, like inductors electrically, and they obey the third equation. You can see that these things are all related to this fundamental variable Q and the driving force, the effort thing, E on the right-hand side. And in particular, what is interesting and easy to deal with is when the constant, the R, the K, and the L are actually constant rather than being variable, which gives you sort of nonlinear behavior. Okay, now we're going to put these things together into graphs, so we need more than that. We need sources of energy, so this is the effort source, or you can look at it sort of dual, if you like, which is the flow source. And the interesting thing there is that both of these sources only define what happens to one of the variables, leaving the other one undefined, because it's the rest of the system that these sources are connected to that determine what that counterpart, the counterpart variable, is going to be. Okay, now there are things that aren't going to play much role in this talk, but just for completeness there, things called transformers. These are basically like electrical transformers, so there's trade-off between what proportion of the power goes through the effort and which through the flow. And there's also gyrators, which do the sort of other thing the other way around. So a change in effort is reflected in a change in flow and corresponding vice versa. Okay. So using those devices, you can't create complex graphs yet. You need something which involves at least three things together so you can loop things together properly. And so we have junction devices. And bond graphs stylize these into two typical types. They're the common effort devices, where you have a load of things coming in and they share the same effort, and the sums of the flows on those connections adds up to zero, so energy isn't created or destroyed in these things. And then the dual of that, the common flow device, where all the flows are the same and the efforts add up to zero. Okay, as it says there, having n at least 3 allows you to create non-trivial graph structures. Okay, as well as that, you also need a technicality positive power directional indication of some sort, so that you know the two devices that you can get to connect via a bond mean the same thing by positive power. Which direction is it flowing? Is it going from this device to that device, or vice versa? You need consistency. Okay, so here's a little example, a very simple electrical circuit there. There's a source of voltage, an inductor, resistor, and capacitor. Underneath the corresponding bond graph. And the striking things it says on the bottom is how different these things are. And this is the thing that is actually, to me, most interesting about the bond graph formalism, in the sense that it says, well, here's a completely different depiction of the same system. And difference is always useful in human engineering design, right? It's the human being that decides what system is actually needed, and having lots of different views of the same thing which look very different can be helpful in confirming that actually you're trying to design the system that you need, as opposed to some consistent system which may satisfy some completely different requirements. Okay, so you see the same components. The source of effort corresponds to the voltage, and then there's the L, R, and C. And they're connected by an effort junction because they all share the same voltage across all three components. Okay. Right, so that's the general idea. And now we're going to sort of start formalizing this thing. So what I call the typing machinery at the top of the slide essentially corresponds to, if you like, meta-model type information, things that are generic across all components of the same type. So we're going to have vertex label there, and you can see the sort of menagerie of symbols that we've already had before there. And for each vertex label, we have a set of port labels. Okay, so this specifies how many connections are connected to each instance of one of those things. Okay, and then we need some typing information. So for each port of each vertex label, you need to say what dimensions and units and so on it has, so that you don't connect the wrong things together. And we add a directional indicator too, so that we can get the directions sort of compatible. So that's the meta model level. At the actual model level, the graph machinery here, we have an undirected graph, vertices and edges, but information will be specific to the port that these things connect to. So we need to be able to talk about edge ends as opposed to just an edge as a member of a set of edges. Okay. And then the crucial thing is the map from the vertex to the vertex label set, which says for each vertex, what kind of device it's representing in the graph, okay? And automatically, once you have such a mapping, you inherit all that stuff from the sort of meta level model up there. Additionally, you need to have per vertex information. So each vertex has to have its own individual effort and flow variables, because not all resistors in the circuit will have exactly the same voltage, right? And so on. And also you'll have the constitutive equations which say how that particular device instance behaves. And the totality of all these equations that you gather together gives you implicitly at least the behavior of the system, okay? Now, I'm suppressing all the details that are in the paper, but you need a strong bijective correspondence between the edge ends in the graphical structure and the ports and properties of the devices, so that your graph actually reflects what the physical requirements are, okay? And here's a little example. So back to the thing we were looking at before. If we just focus on the resistor, then up at the top, the first line gives the generic information. So its port label, its vertex label is a big R. It has a single port, that's just little r, obviously redundant, strictly speaking. And it has a directional indicator which says power goes into a resistor and gets dissipated as heat, okay? The second line talks about a specific vertex, this thing called VR, okay? So it says that the vertex VR is a device of type capital R, dissipator in other words, and therefore it inherits the dissipator port and the dissipator directional indicator. And the line below gives you the vertex specific stuff. So V .R.R.T, that's the effort variable for that particular resistor, talks about the voltage going in. The next thing is the flow variable. And then the last thing is the constitutive equation, which is just a complicated way of saying voltage equals resistance times current, okay, in the case of an electrical resistor. And the same for all these things, all the other things in the circuit. Okay. Now, what's gone on there? So, as it says, if you it's obscure like the menu bar, what it's supposed to be saying is, if you take this correspondence between physical properties and what is represented in the bond graph seriously, then there's little scope for sort of non-trivial homomorphism, non-trivial morphisms. Now, what we're going to do is sort of see what scope we actually have. If we're going to have homomorphisms of bond graphs and they're not to be just isomorphisms, then you need some kind of wildcard mechanism so that they can be injected as much as they need to be, but you can stop the injection at a certain point so that you can talk about part of a bond graph instead of all of it up to isomorphism. Okay, so we introduce this any label, which we represent by a blob like that. It's got stuck now. Okay, So we get the idea of a pattern, which is a bond graph-like thing containing 0 or more any devices, and it's like a proper pattern if it has at least one any, okay? And the rules for matching, summarizing briefly there, non-any vertices have got to match completely injectively. You've got to preserve all the properties. Edges and, importantly, edge ends must also match injectively without loss of any properties. The only thing that needn't be injective is any vertices themselves. Okay, so and they just need to preserve basic information, type compatibility. Okay, so here's a picture of a matching. The thing above is a pattern with two any's sticking out. And that's matched to a bond graph, which has a piece that looks exactly like that. But there's this vertex here, which is the target of the matching for both of the any's, okay? Now you notice that there's two edges incident on that note. There's two separate edges in the pattern above, okay? So we can preserve the properties at the ends of those edges in the way that we'll need for type compatibility, okay? And now we can move on to bond graph transformation. This is basically patterned after the double push-out construction, but with a tweak, okay? So if we have morphisms in this category, which I've just been describing, okay, we can describe transition rules, transformation rules, and how you apply them. A rule is this thing that you can see there. It consists of two patterns and P in the middle, where P, as it says there, is a type correct bijection between the any nodes or the any vertices of the two patterns left and right. And applying the rule is kind of what you would expect, having mentioned double push-outs already. The way you actually do it is you remove from a graph to which you're applying the rule G, okay, you remove the image of L except for the matches of the any's, you're keeping those there, okay? And then you replace the stuff that you've taken out by a copy of R, again missing out the bit that's identified by P, because that's already remains there from the bit that you stuck before. As it says there, this is a kind of illegal double push out, because after you've done the first of those two steps, you end up with something that isn't a bond graph, because in general, it's going to have dangling ports, if you like, okay? You've taken away the things that maintain the invariant, so ports must match bonds going in and out, right? So temporarily, you sort of break the invariant and replace it by the stuff that you bring in from R. And here's a sort of picture of that in the sort of extending the stuff that we had a slide or two ago. So we got two patterns L and R. You can see P, which is just the bijection between the any's, and that maps to this thing that we saw previously, and you simply replace it by the thing on the right-hand side, which fills that hole, okay? And because of the way that we've sort of stipulated injectivity and bijectivity, the type information at these two sort of edges matches the type information there. That's bijectively the same as the type information on the corresponding thing for the R rule, and that bijectively matches the thing in H. So we have correct properties of the resulting graph H. So that's actually pretty straightforward. Okay, so let's look at a few example rules here. If you have a bunch of constant effort devices connected, something like that, you can reduce it to a single one, or you can short circuit a single one of these with just two bonds to a straight through thing. As it says just below, these are sound and complete. Now, I haven't talked about soundness and completeness yet. The semantics, as I mentioned briefly, I think, is a set of all behaviors that are solutions to all this huge bunch of equations that you get when you gather all the devices in your system, okay? So soundness means that anything in the right-hand system must be something that could have been obtained from the left-hand side system, and completeness is the thing the other way around, okay? So it's clear because the rules for these constant efforts vertices are so simple that it's clear that soundness and completeness actually follows. Here's some more. At the top, we see a rule that crops up a lot in bond graph textbooks, okay? So you have this sort of diamond shape there and sort of 4 any's or 4 connections to the rest of the world there. It turns out that you can rearrange this thing into this shape on the right-hand side. And you can keep track of which any is which by simply looking at the flow and effort variables that decorate the bond that it's attaching to. So you find the same 4 flow and effort pairs in the left-hand side diagram and in the right-hand side diagram. Underneath, you find an application of that rule. It doesn't immediately look the same, but you can see the diamond shape in the middle. The thing sticking out on the left in the rule is sticking out into the middle to save space. And I've sort of joined the top and the bottom to a fictitious D device that happens to have 2 ports there. And if you apply the rule and make the change, then you actually end up with the shape on the right-hand side at the bottom. Okay, so these are perhaps not terribly serious examples. The most important application is this thing here, which is abstraction and refinement, okay? And we illustrate this with an example, okay? This example is an example of an electric motor, if you read it from left to right, and it's an example of a dynamo if you read it from right to left, okay? So electrical power goes in from the left and there's some losses and some stuff happens. There's a gyrator that turns it into rotational motion and there's inertia to do with the weight of the drive shaft and its angular momentum and so on. That's a sort of complicated, detailed definition of the motor, but if you want to use the motor as a component, you can use the sort of graph transformation formalism to replace it with something on the right-hand side, which is a single user-defined symbol, and the formalism says what attributes it needs to have in order for all the formal properties to work. And this M/D device is just a single thing with 2 external connections, which is what the motor has. And all the internal detail of the complicated diagram there, and in particular, the parameters which are in round brackets there, specifying the properties of all these internal devices, they all become parameters of this user-defined label, okay? And now you can use that in any context where you can legitimately use the big diagram. So that's abstraction. The converse would be refinement. You can have a big library of these things, right, with appropriate properties, but when you come to build them in practice, you replace them with the detailed bond graph there, and that's the system that you construct, okay? So that's kind of the punchline. I'm just about on time. So here's the conclusions, okay? I think, and some people at least think, that bond graphs provide an interesting alternative view on systems. And as I say, in human-oriented design, it's always useful to have a different perspective, okay? The existing bond graph literature, as I'm reassured by your comments earlier, is appalling. It's full of inconsistency. And I mean, John and I are both native English speakers, so we sort of flatter ourselves we should be able to understand what's written in English about this stuff. But we both kind of reached the conclusion when we read some stuff, what on earth does this mean, right? And this is the sort of object of the exercise behind our work, and to build a framework for this which people can actually understand without joining the cult, if you like. You can actually read it and understand it, okay? So that's what we're doing via graphs, transformations, and the combinatorics that's behind it, okay? Now, the bad news is that what I told you about is the easy bit, right? It's just the sort of power level version of bond graphs. There's a whole sort of further industry to bond graphs, which is they refer to as causality and so on. And it's the business of deriving strategies for solving all this bunch of equations that you generate by sort of collecting all the devices together, and how do you actually solve it, right? And that gets quite messy. And that really is where the obscurity in the literature lies, because basically it's poorly defined. There are rituals that you need to obey. And when you start getting into it, there are fairly trivial counterexamples you can construct where it breaks down, okay? So this is what we're busy with at the moment. We're sort of trying to fix this, get a perspective on that aspect of it that makes some sense with the kind of rigor that would be acceptable here. So I'll stop.
Thanks. Plenty of ground for discussion.
But there are related notions, related notions of graph, one graph. You mentioned boards, sometimes graph that is there are these graphs in chemical modeling, the cover graph. I think if you look at the structure overall, the basic idea is the same. But for example, in the cover graphs, they have a specific application condition if you rewrite them. So you have essentially if you have a board or a site, as it is called, and that is not that is mentioned in the rule, in the note in the rule, but it's not connected to anything, and you cannot connect that to anything in the in the host graph. And the idea of that is, I think, that you want to be able to say this is it's an open it's an open
an open system, or something.
It's a free not a free, but it's a free connection.
Yeah.
But that is a connection where you want to say this is free for something can connect there, but currently there isn't anything connected there. So we have an implicit negative condition that comes with having reports or not connected in this way. But I don't think we have that.
No, because, well, basically, the purpose of the sort of kappa graphs, as I understand it, and this are rather different. There you're talking about chemical reactions and change and so on. Here, it's mainly a static description of a system. Do you understand the design? You want to illustrate it in this way for, requirement satisfaction and generation of equations or whatever you want to do. So you can use the transformation stuff to replace one piece of functionality with another. That's the whole thing, but then you don't have any invariance, you don't have any sort of soundness or completeness aspects to it. The nice thing about the abstraction stuff is that you can actually argue about the soundness and completeness, because that one, we go back to here, essentially how you get this description from this description is you just existentially quantify, right? So it's clearly going to be sound and complete. So that ties up the kind of properties that people here are interested in with what goes on there. But there's a whole other aspect of it, which is basically less interest to sort of graph transformation per se.
Yes.
So it's somehow following up on that question. So there are some tools that are based on the idea of core graphs that they're a bit similar, not exactly the same, but which might help. I understand you are not particularly interested in the dynamics, but it might be the case that some of these you showed us a couple of rules. Maybe
that was actually a number of tools that deal with bond graphs specifically. I mean, one of the most well-known one is conference trends. It's called 20SIM, right? 20, right? You get it. And there's a big European project which created a tool called Modelica, and there are lots of older tools as well. I mean, there's a whole bunch of these things. Now, it's clear, if you just sort of think about it for 5 minutes, that what they're doing behind the user interface is somehow equivalent to something here, but none of that is ever written down. So if you're coming to this stuff fresh, you're just left with this mush of English that doesn't quite add up. So, you know, it's sort of, so clearly the people who write the tool understand what they're doing, right? Otherwise the tools wouldn't work.
I think I wasn't clear. I meant graph tools, so general purpose graph transformation tools, like for example, forming, where you can define your core graphs. It doesn't need to be one graph. It's a four graph. Forming doesn't care what kind of thing it is. So you have those sort of tools. That's what I was referring to.
No, I was saying lots of more specific ones because these other tools actually do simulations of the system, solve equations. I think what they do, you know, in the face of all this inconsistency I've been talking about, if they hit something that they can't do, they just give up, right? And so they do some cases that they know how to deal with and, you know, forget the rest. So that's the sort of typical thing.
It does beg the question. So you've done this. You're an outsider to the cult.
Yes.
Your co-author is a heretic.
Yes.
Is this work actually accepted in that community? I mean, do they see the value of what you do?
It's not. Well, we haven't published it in that community yet. This is the first publication of this work. So particularly, well, as I say, we did the easy bit. So this is kind of it, right? So that bit's complete. But the more, in many ways, the more important bit is delving into this other stuff. And it's only when that's sort of sorted out and we've written it up properly that, you know, publish or the biggest.
I'm wondering, are you in communication with these people, for instance, from whether they find the sort of thing you're doing in principle interesting, or they already say, yeah?
Well, I mean, the answer, the short answer is no, in the sense that we're trying to understand it for ourselves, right? If we understand it and we can convince ourselves that the mathematics is consistent, then we have a story. Otherwise, it's just vagueness and more vagueness. Yeah.
I was preempting the audience. Any more questions? If not, then thanks again. Come for lunch before Tuck gets there.